Was that enough time? Who's got the number of hydrogens for the molecule on the left? Kirsten.
Oh.
9? Anybody disagree? Who agrees? Raise of hands. You got a lot of the class behind you. Good. So here's a carbon, and it has one line explicitly shown. We know that carbon wants how many bonds? 4. So if 1 is shown, it must have 3 more, so that's 3 hydrogens. And again, with bond line structures, we can abbreviate that as CH3. We can assume that it's a CH3, or we can show that it's a CH3. But what we shouldn't do is just show a C or just show an H3. If you're going to assume one part, you should assume both. If you're going to show one part, you should show both. Okay, then we've got a CH3 here, CH3 here. What about in this central carbon? 3 bonds explicitly shown, correct? So it's missing 1, which is why it has a positive charge. It has a positive charge because it only has 3 bonds. Remember, this can be calculated by 4 minus what will give me a positive 1 charge. 4 valence electrons for carbon. If there are only 3 bonding regions, that will give me a positive 1. So there is no hydrogen at that central carbon. Deal? All right. So 9 hydrogens in this molecule. 3, 6, 9. Somebody else for the structure on the right. How many hydrogens? Hamza.
11.
11? How many here? 3. And then 2. And then 2. So that's 3, 5, 7. I don't think we're going to get to 11 because we'd need a lot more. How many hydrogens here? This is the debate between 2 or 3. It's an end. So you might think that it's a CH3, whereas these were in the middle, CH2 groups. But because this has a negative charge, that's going to take the place that a bond to a hydrogen could have had. So this will be the opposite equation. 4 minus what equals negative 1? Well, you might say 4 minus 5. Okay, carbon's not going to have 5 bonds. Can we agree to that? And in that table that I had you guys build during that first week, we saw carbon with a negative charge always holds a lone pair. So that negative charge on carbon, let's just reiterate it as a lone pair. Now, carbon has 2 electron regions explicitly shown, the bond and the lone pair. So how many more electron regions until it's full? Just 2. So this is a CH2 group as well. 2, 4, 6, and 3 gives us a total of 9H. These are not isomers of each other. These have different chemical formulas. They both have 4 carbons. They both have 9 hydrogens. But the one on the left is C4H9 plus versus C4H9 minus. So they are redox versions of each other. One is more reduced, one is more oxidized, in addition to their carbons being bonded in different ways. Same number of hydrogens, though, and that's the interpretation I wanted you to get from that practice problem. Jordan, you wanted to look at structure number 4 on our worksheet, right?
Yeah.
Let's look at it. I gave this one to you as the bond line structure. And do you have questions on how to convert it into condensed molecular structure? I'm sorry, I gave it to you as the Lewis structure. Do you want to talk about condensed, bond line, or both?
Bond line.
OK. Sorry, let's go through both. We've got this huge ring on the left, and we said that we can abbreviate that ring, correct? That 6-membered ring with alternating double bonds can be abbreviated as C6H5. So that's how we'll draw it in the condensed molecular structure. Then I've got this C double bond O and a CO group coming off of it. And we said that when I have a C double bond O and an O coming off, I can write this as COO, or I can write it as CO2. Both are perfectly acceptable. Those are condensed versions that I want you to be familiar with.
Is this where we need to put the parentheses around one of the O because it's only bonded to the carbon now?
No. That instance of putting the O in parentheses is when the carbon double bonded to O has carbons on either side.
Okay.
We had 3 instances. We had a C double bonded to O with oxygen on the side, and we abbreviated it this way. We had a C double bond O with a hydrogen on one side, and we abbreviated it as CHO instead of COH. And the carbon double bonded to O with carbon on both sides, put the oxygen in parentheses. Now I can continue describing the rest of the structure, and to condense all of this, there's one carbon that has 3 CH3 groups connected to it. So I have to describe that first C, that central carbon, and then explain that 3 CH3 groups are connected off of it by putting those all in parentheses. Okay, bond line structure. We show that 6-membered ring. We don't show any of the carbons explicitly. We don't show any of the hydrogens explicitly. We have to explicitly show the oxygen heteroatoms. What do you think?
Well, yeah, that makes a lot of sense. However, in the homework, it does not let you do that, as far as I'm aware, unless somebody can.
Is there a specific problem it's not letting you do this on?
Yeah, number 15.
Let's look at it. What other questions while I get this pulled up? What other questions do you guys have?
Can we do number 2?
The second structure?
Yes.
Yeah, this is a challenge, and I gave it to you for that challenge. So we start with the condensed structure, CH3, CH, CH, C, CH. There's not a lot of H's there in the right-hand side of the structure. All right, and I'm sorry, Jordan, 15 you said?
Yes.
Oops, sorry, I got to do this the other way. All right, so with problem number 2 on our worksheet, CH3, CH, CH, CCH. I'm going to start maybe by doing this in the Lewis structure form, since I know how many atoms I have, but I don't really know what those bonds look like. Once I know the Lewis structure, then it might be easier for me to just simplify it into bond line. So CH3, straightforward, a little cumbersome. CH, CH, C, dang, CH, correct? All right, that's obviously not full octets at each of those atoms, right? So if I went through with the molecular formula and I found out how many valence electrons I need to have, I would realize that I do not have all of my electrons shown. I'm short by 2, 4, 6 electrons. Okay, but I don't really need to know that I'm short by 6 electrons to recognize that my octets aren't met. So let me take the atoms that I know are there and meet their octets. This carbon on the right only has 2 bonds. It needs 2 more. It can't give any more to the hydrogen, so the other 2 bonds must go to the carbon on the left. These 2 carbons each have 3 bonds shown. They each are lacking 1, so I can give a double bond between the 2 of them. Now this is easy for me to show you, but recognize that you beginning may not realize where you should put these bonds. Because here I see a carbon with only 2 bonds and a carbon with only 3 bonds. And so I could satisfy the carbon on the left with a double bond. And now the carbon on the right is close to being satisfied. Now it is satisfied, but now this carbon on the right can never be satisfied with an octet, because I can't make another bond to hydrogen, and this carbon won't be satisfied. So that's a bit of the struggle that you have to go through to decide where do I want to place all of these bonds such that the structure is satisfied easily. Now that we know this, I've got a single, double, single, triple. I can translate this into bond line structure. Single, double, single, triple. CH3, CH, CH, C, C, H. There's a lot of ways that you could draw this, and this doesn't have a lot of information in it. So there's technically a lot of correct answers. What I suspect a number of you probably would have shown me is something like this, where this triple bond group is in a zigzag formation. The problem is that this is an sp hybridized carbon. What geometry at an sp carbon? Linear geometry, not bent. So it would be more appropriate to show it linear to its other bond. I wouldn't mark this as wrong. Truth be told, when I look at my OCHEM 2 notes and we drew alkynes, this triple bond group, I drew them zigzagged. I drew them without linear geometry. So it's not something that I grade on, but it is something I want you to pay attention to, having that triple bond linear to the groups coming off of it. You don't seem satisfied with that. Is this what your question was?
Yeah, I just drew it originally, and then as you drew that out, I thought, oh shoot, hydrogen can't triple bond, and that makes it look like the hydrogen is triple bonded.
No, it doesn't. It doesn't make it look like the hydrogen is triple bonded because it's a carbon at every end and bend. So here's an end. That's a carbon. How many bonds does that carbon have? Just like this question up here. Well, it's got 3 bonds explicitly shown, so it must be missing 1. It's the 1 to the hydrogen. Or again, we could show it as a triple bond to a CH. Here's the deal. I'm not invalidating your experience that it seems like the H is triple bonded, but you need to remember the assumptions, remember the rules, and the best way to do that is to start interpolating between these two forms. So take bond line structures that you're seeing and start adding in the hydrogens that are assumed. Start to get familiar with where hydrogens are and how many hydrogens there are there. Take bond line, add the hydrogens back in, because I don't want you to forget where those hydrogens are. The more you do that, the less you'll need to do that. Deal? All right, let's look at this problem, problem 15. Oh, I should have pulled it up earlier so it could load. What other questions did you guys have from this one? How about number 3? There's an interesting condensed molecular formula for number 3. You're given a bond line structure like this, and some people will abbreviate this with this condensed molecular structure. Oops, no, not quite. A subscript 2 after the parentheses, because there are 2 of the CH3, CH2 units bonded to the O. Personally, I don't like it. It makes it look like there are 2 things on the left of the O rather than 1 on the left and 1 on the right. It's a bit trippy. Number 5, I want to show you guys how we can abbreviate it. Number 5 can be abbreviated as CH3CO2H or CH3COOH. Number 6 can be abbreviated as 2 CH2 groups connected to a CH group connected to a CHO. And this is the one that I would remind you not to put it as COH, because it will mislead your thinking about what is being bonded there. I should have given you the true, what I think is a better way to abbreviate this one. CH3, CH2, O, CH2, CH3. I think this is better because it highlights what two groups are on either side of that oxygen. And having the oxygen with two carbon groups on both sides should give you this idea of having an oxygen linking these two carbon groups, which is why for number 7, we don't just put an oxygen. Instead, we put the oxygen in parentheses. So for this, you were given CH3, CO, CH2I. Here's a CH3. That oxygen in parentheses informs us that it's double bonded. It is only bonded to this carbon on the left. It is not bonded to either of the other carbons. And then a CH2 with an iodine coming off of it. Do you guys recognize that at all? How many of you took Gen Chem 2 here? Or are taking Gen Chem 2 lab? There is an experiment in the Gen Chem 2 lab where you take acetone, iodine, and hydrochloric acid, and you run a kinetics experiment. You decide what concentration of what chemicals will actually change the rate of the reaction, and you make iodoacetone, which is what this compound is. I think that's always a fun connection, to take something you did in Gen Chem 2 and relate it to what you're learning in OChem 1. Sorry, Jordan, I don't think we will be able to do your active problem. Okay, and then the last one, number 8, I actually put on there as a way of showing you that not everything is always best represented in bond line structure. So the condensed molecular formula for 8, CH3CN. Great. That's how most people represent it. Its bond line structure would look like this, which is weird. It is a little bit, I guess I would say it's a little bit more cumbersome to draw it on the bottom than it is on the top. And it's a bit confusing as well. Okay, here is why this won't let you abbreviate it. Or, sorry, is this your question? Why won't it let you abbreviate it as C6H5?
No, I was able to get most of it, but the sulfur atom in the middle, like, I believe has to be bonded to 4 different things, but it doesn't fit on the lines of like the, I don't know if anybody else had this problem.
I had an issue with it, but once you do it, there's this secret little line that pops up. Yeah, it'll
Oh, I guess I
pop up.
never found it.
Shoot.
No, it's really weird. It took me 20 minutes to do it, and I was tried. But there is a little line that pops up eventually. That'll let you do it. See if it, yeah.
What?
It did show up as this like light gray. And it lets you do that 4th bond. Is that all that was missing? And who else has done this and knows whether or not they're going to ask for lone pairs? Oh, they don't give you the lone pairs, so never mind. Here's what I find the most challenging about active. Every time you click on a bond, it will give you like every combination of where atoms can sit in those bonds. So for instance, this option here shows placing the sulfur at the top. And this option here shows placing the sulfur at the bottom. And it orients you by that red line on the bottom as to where it's going to show up relative to the line you've selected. That to me is more confusing than being able to just click at an atom spot and place the atom where you want it. So I do apologize for that throughout the semester. But again, the more you use it, the more familiar you get. And this is just a tool to help you showcase your understanding of other things, not your understanding of technology. So if you get really burdened by this, then just send me your handwritten work and say, I can't get it to give me the right answer. And if it's right, I can automatically update your grade for you. Okay? Because your job in this class is not to learn how to use active. Your job in this class is to learn organic chemistry. Okay, good work. What'd you think? Now, how many of you flipped this over the weekend and did the top on the back? This is something at this point that I believe you can do. So this is split kind of into two things. There are these structures separated by arrows, these 3 rings. What I want you guys to do for the next 5 minutes is in groups, add charges based on the lone pairs that are shown. You don't have to do anything with the carbons. All of the carbons are satisfied. But work with the chlorine and the oxygens in each of them. Based on the bonds and the lone pairs shown, add charges. The last 2 structures, I want you guys to go through and add lone pairs that are missing. This should feel a little bit like this first problem. Based on the charges that you see, fill in any hydrogens or lone pairs that are missing. Deal? All right, spend 5 minutes placing charges and lone pairs on that back page. Everybody's got theirs? Can I give anybody else one that's missing one?
Thank you.
Mm-hmm. Carla, I'm sorry I didn't say hi more nicely downstairs. I didn't recognize you. I was like making this. I had to rush to my office to print it. And I was like, what? Who said that? I know, I felt so bad. Which?
Those. What's coming at you? That was coming towards you, right? And that one's going away from
That's
you?
right.
Okay.
Yep.
Which you would think that like a wedge would be like a shadow and it would go away from you.
Interesting. Do you know what? I should have you consult with the powers that be around chemistry. I think the dash is meant to say it's fading away.
Yeah.
And the wedge is meant to say it's bold coming at you.
Yeah. And if you like paint, like the things that are like if you have like a scenery, what's far away is gonna be like more faded.
Lighter. Yeah. Yeah, that's a good point.
Because it was due before I added the class and I will go back to find it. So
Mine was sitting there.
You're welcome. You bet. Sorry, that wasn't actually for you, Britton. Now you're welcome. You bet.
So it still is, it's short, so it would be possible.
Oh, you're adding the sorry, yes.
What is this place partial charge? That one's either, but this one is going to have something.
Because the cells are low.
Kirsten, what has 2 valence electrons?
Sorry, I don't know if I'm saying the right thing, but it's magnesium.
Oh, okay. Magnesium, calcium, beryllium, they have 2 valence electrons.
What I meant to say was that they can make 2 bonds.
There you go. There you go.
And I know that in my brain, but you're right. It's the wrong thing, and I should-
So on this one,
Mm-hmm.
I get that it's positive.
Yeah.
Where would it wouldn't have lone pairs?
There you go.
So you just don't do anything?
Yep. I want you to feel comfortable with that.
Because I had that question up there. So where does that, like, what happens to those electrons? Because it has 3 single.
Called home. Well, what electrons? What do you mean? Maybe there never were electrons. The real answer is there's a lot of ways that you can make that chemical. Sometimes you have a carbon-carbon double bond, and the pi electrons from the double bond leave, and they leave behind an empty spot on the 1 carbon. Other times you have a bond between carbon and a halogen, and the halogen leaves, and it takes the electrons from the bond, and it leaves behind an empty spot. So I think what you're getting at is what's balancing the charge. You can't have a cation without an anion, but it doesn't matter. Right now, I just want you guys to become familiar with the structures and look at that and say, done. I don't need to add anything. All right. Who can tell me whether there is a charge missing on our first structure? Also, how comfortable are you guys with cold calling? Like if I just point at you and
I thought you meant like a solicitor. I was like,
what if I give you the right to say no or pass? Then can I call on your name? Oh, all right, fine. Who wants to tell me what charge is missing? Britton? On what? The chlorine has a positive charge. We know that because it has 2 bonds. We can prove it by taking 7 minus 2, 4, 6. 2 bonds and then 2 sets of lone pairs. Every line and every dot counts against it. Okay. What about my second structure? What is missing? No? Jordan, do you not agree?
How'd you get 6?
7 minus 1 line, 2 lines, 3, 4, 5, 6. I've got 4 dots. That's right. I count every dot and every line. Or you can count half of the bonding electrons and all of the non-bonding electrons. Half of the bonding electrons is just each bond. Okay, what about my second structure? Where? Oxygen holds a positive. Here, I've got 6 minus 3 bonds and 2 dots, so that's 5, leaves me with a +1. Oxygen with 3 bonds holds a positive charge. Oxygen with a positive charge has 3 bonds. That is the ABCs that I want you guys to be familiar with, because that means you can look at a structure and more readily apply charges. What about my last structure? No charges are missing. This is neutral. Good. The goal of this class is to learn about chemical reactions, organic reactions, and more specifically, synthesis pathways, taking something through multiple reactions. And this is a reaction we'll learn about later in the semester, including that wedge and that dash stereochemistry, showing you arrangements in space. So as a review, for those of you that didn't quite remember, wedge means towards you, and dash means away from you. Good. All right, how many lone pairs missing from this cation structure? I heard somebody say it, but they didn't raise their hands. No more Britain. None. There are no lone pairs missing. So I do want you to feel comfortable being asked to solve a question like this and saying it already is good. That is okay to say everything is already shown. This has nothing to be added to it. What about here? The oxygen. I'm only going to call on you once on a problem set. Christine?
Well, I have a different question.
Sure.
Why would we put a charge on the carbons?
In these structures up here? So confusingly, I probably should have shown that this is a CH, this is a CH. So they have all of their bonds. This was only meant to show you the hetero atoms, the oxygen and the chlorine. So there are no charges missing from any of the carbons because they have their bonds. To be fair, you weren't shown that they had all of their bonds, so it would be impossible to know. Well, actually, we could take one assumption. The wedge and the dash only appear on sp3 hybridized atoms. The wedge and the dash represent three-dimensional character. So in order for this to have a wedged group or a dashed group, it must be sp3. To be sp3, it must have 4 bonds. That 4th bond would actually have to come from the hydrogen. And if we don't see the hydrogen because we assume it, we also don't see the hydrogen's wedge or dash, but we can assume it. We already have 2 bonds that are in plane. We're missing the dashed group, so that means there must be a dashed hydrogen here. There must be a wedged hydrogen here, and a dashed hydrogen here. So we could actually use the stereochemistry to inform about that, actually. Great question.
So what do you have, 6 lone pairs?
Yes and no. Pairs.
Like three pairs.
Good. Yes, 3 lone pairs, 6 non-bonding electrons. If I've got 6 minus something to give me -1, that something must be 7. The bond that's explicitly shown is already included, so that would be 6 dots and the 1 bond. Great. All right, that is all of section 1. Hopefully you've already been able to complete the homework, but if not, this should have given you that catapult to finish. Partial charges actually begins our section 2 discussion. And partial charges are important because they help us predict chemical reactivity, how a reaction is going to proceed. So in order to predict partial charges, we need to understand electronegativity. Can anybody define electronegativity?
It's like how, it's kind of like, I think of it like magnets, how they, gosh, how can I not?
Are you a strong magnet or are you a weak magnet?
Yeah, as you go up and towards the right of the periodic table, they're more electronegative. So like fluorine is really electronegative, and it really wants an electron to come to it.
Good.
Electrons are more likely to go to it.
Good. Absolutely. I mean, do you guys agree? Think of electronegativity like magnets. The higher the electronegativity, the stronger it pulls on the electrons towards itself. And generally, this increases up the periodic table and over to the right. And I say generally because fluorine is listed as the most electronegative atom, but helium is further up and to the right than fluorine. And helium does not have an electronegativity value. It does not pull on electrons. It's just incredibly stable on its own. So generally, up and over. So there are a few important places on here. Oxygen being just to the left of fluorine makes it the second most electronegative atom on the periodic table. Then nitrogen, then carbon. Underneath fluorine, chlorine, bromine, and iodine. And there may be some instances that we look at sulfur and phosphorus for electronegativity. But generally, we look at this corner edges. Carbon through fluorine, fluorine through iodine. Electronegativity is that pull on electrons. Affinity for electrons. So, if two atoms are bonded, covalently bonded, meaning they share electrons between them, but they have a difference in electronegativity, then we can predict partial charges. If the difference in electronegativity is less than 0.4, we call this a nonpolar bond. If the difference in electronegativity is greater than, I think I have to show it this way. If it's greater than 0.4 but less than 1.0, you guys remember what this triangle means? Change. Yeah, this is delta. So we're talking about difference, the difference in electronegativity. If the difference in electronegativity lies within this range, 0.4 to 1.0, we call it a polar bond. And anything greater than 1.0, ionic. Do I have that wrong? I'm thinking it's 2.0 or 1.5. Well, let's find an answer. Here's the deal about this. That is a made-up benchmark. 2. I think it's 2. I don't know why I thought it was 1. I believe it's difference in 2. Yes?
Electronegativity is greater than 0.4, right?
Yeah, so if it's greater than 0.4 but it's less than 2, it lives in this realm of being called polar. So we have defined these groups. Maybe it is 1.5? Nobody agrees. Great. Because it's all made up. Yeah? Scientists said, look at this bond, and the difference in electronegativity is what we'll set the benchmark as. The CH bond has a difference in electronegativity of 0.4. So they set 0.4 as the benchmark for nonpolar so that they could call CH nonpolar. Nature does not recognize polar bonds versus nonpolar bonds. Nature recognizes a spectrum in difference in electronegativities. We have set these boundaries. Are you comfortable with that?
So what's your boundary?
My boundary is, it doesn't matter what you call it. There are predictions you can make regardless. So I have this large molecule. And you know what I'm missing? I'm missing a CH bond. I have bolded, and I do want to point out this is bolded, not wedged. I have bolded different bonds that I want us to place partial charges on. And what I need you to do is add in there a CH bond. According to this rule, and honestly I should have just shown it like this, nonpolar, polar, ionic. If we follow this rule, then we say that the CH bond is nonpolar. So we would not place partial charges. Okay, but is there a difference in electronegativity? Yes. How does that difference in electronegativity distribute itself? Which atom between carbon and hydrogen is more positive? Which is more negative? Carbon being further to the right on the periodic table is more electronegative. So these these electrons shared between the two are not shared equally. They're actually held by carbon more than they are by hydrogen. That nonpolar bond has a distribution of charge. It's just such a small distribution that it doesn't really impact its reactivity compared to other bonds, but it does still predict its reactivity. It's not a partial negative hydrogen. Are you comfortable with calling this a nonpolar bond and placing partial charges? Are you comfortable with it? Or does it make you uncomfortable? I'm comfortable with it because everyone else is going to call it a nonpolar bond. But it has partial charges. Okay, now on to the more interesting and common bonds. First, we have the CO bond. The CO bond has a difference in electronegativity greater than 0.4. I think it's closer to 1.0. So the CO bond gets labeled as polar. How is the electronegativity distributed? How should I place those charges? Where is my partial negative? On oxygen, which is further to the right compared to carbon. More electronegative, less electronegative. Partial negative, partial positive. What we're doing right now is creating special magnets. If electrons are going to be pulled towards this molecule, electrons will get pulled towards where it's partial positive, where there's a low electron density. If electrons are going to leave this bond, they're going to be leaving with the group that's pulling on them. Okay, do you remember this symbol? That's delta. It's lowercase delta, and we say delta positive, delta negative to say it's not a formal charge. It's just an excess of electron density a little bit, or a deficiency of electron density. What about a CO double bond? How should I place partial charges?
Does the amount of bonds ever affect that?
Good question. Does the amount of bonds affect the placement of partial charges? Does the amount of bonds change the difference in electronegativity between the two atoms? Nope. So if the difference in electronegativity is the same, then the partial charge character is the same. If the difference in electronegativity is the same, the partial charge character is the same. So C to O single has the same partial charges as C to O double. C to N, polar bond or nonpolar bond? Now, here's the deal. You could get a table of electronegativity values. I think that's just going to slow you down, so I want you to be familiar with this. Also polar. This has a difference in electronegativity of about 1. Where am I going to place partial charges? Partial negative goes where? Nitrogen. Partial positive? Carbon. What about a double bond to nitrogen? All the same. Partial positive on carbon, partial negative on nitrogen. All right, let's look at some other bonds to hydrogens. How should I place partial charges? If we can agree that carbon is more electronegative than hydrogen, and the difference between carbon and oxygen is polar, then the bond between O and H will be polar, and we'll have partial charges. Where should I put the partial negative on the OH bond? Oxygen. The second most electronegative atom, remember? What about an NH bond? Polar bond or nonpolar bond? Polar. Partial negative? Nitrogen. Okay, let's look at a couple of interesting ones. What about an N to N bond? Should I place any partial charges? No. Should I call it polar or nonpolar? Nonpolar. What about an O to O bond? This is a bond that we call a peroxide. Polar or nonpolar? Nonpolar. Partial charges? No. What about an N to O bond? This one might be one that you'd want to check, but the difference in electronegativity, 1.0, or sorry, I think 0.5, meaning it's just larger than that arbitrary line that we set. So we call this a polar bond. How will we place partial charges? Oxygen is partial negative. Nitrogen is partial positive. Oxygen is more to the right. Why is this all important? Because when we start doing reactions and we have to see electrons break bonds and form bonds, partial charges will tell us how those electrons are going to behave. Electrons are already being pulled towards oxygen. So when a bond needs to break, oxygen pulls them away to break the bond. That's what our partial charges will tell us. All right, and then with all of the halogens, I want to point out something that a student of mine brought to my attention once, which is that the difference in electronegativity between carbon and bromine is about the same as the difference in electronegativity of carbon to hydrogen. And carbon and iodine have the same electronegativity. But I want you to still feel comfortable putting a partial positive on carbon and a partial negative on iodine. If they have the same electronegativity, how in the world can I argue that you should believe that this is a polar bond and that iodine holds the partial negative? Any idea?
Is it when it goes up, it's more electronegative than like lower on the table?
So you can kind of see the relationship between carbon and iodine. Carbon is more left but more up. Iodine is more right but more down. So they have the same electronegativity. There is no difference in electronegativity. So how then can we argue for this charge distribution? Not quite. These all have the same number of lone pairs.
Well,
And you're saying,
with iodine and carbon.
I see. No, I don't think that we can say it's because of the lone pairs, but I like that idea.
Isn't it because all of those have 7 valence electrons, and so they just need one to get 8, so it's more?
Well, kind of the same idea, but does that mean that iodine can really pull electrons away from carbon just because it wants just one more? That carbon also wants to keep the electrons because now it has a full octet. The fact that it has 7 valence electrons tells us that it will have more lone pairs and just less covalent bonds. I'm going to ask you to believe in it because of its size. Fluorine is a very small atom, but it's very electronegative, so it pulls on those electrons very strongly. Iodine is a very large atom, and despite not being very electronegative, if this bond, I know you guys liked to see that orbital overlap, if this bond is the overlap of the two sp hybridized orbitals, of the two sp3 hybridized orbitals, here is carbon's orbital. It's very small because it's a small atom. Here is iodine's orbital. It's very large because it's a large atom. Where are the electrons distributed around the bond more often? They're distributed around iodine because iodine has the larger orbital. Larger size, larger orbital, larger chance for the electrons to be there. And if the electrons are there more often, it's more negative. Are you comfortable with that? And ultimately, this comes down to an idea called polarizability. And we will get to that probably not today, likely next class. We'll come back and touch on this polarizability. The size allows it to polarize itself, and the size of iodine allows it to polarize the bond without having a stronger pull on the electrons. Wild. Okay. All right. Did you get them all? Any questions? These, again, are your ABCs. Being able to look at a bond and place partial charge character. Being able to look at a bond and know what is negative, what is positive. Any questions? Should we take a 5-minute break? Because next, we're going to get into this next worksheet. So let's take a break and come back right after 6 o'clock. Please.
Okay, so I watched a bunch of videos over the weekend
Good.
about orbitals.
Yeah.
Because they were hard for me to understand.
I like that growth mindset. They were hard for me to understand.
Thank you. So carbon is an sp3 hybridized because it can make 4 bonds. And no?
Nope, that's not what determines it.
Okay. Okay.
It can become sp3 hybridized because it can make 4 bonds.
Okay.
But actually, oxygen can be sp3 hybridized
Okay.
with only 2 bonds. It's more about the number of electron regions. How many places around the atom are electrons being stored?
Okay.
Think about water, where the oxygen stores its electrons in 4 different places.
Okay.
2 bonds and 2 lone pairs. In order for those 4 different places to minimize their electron repulsion, it hybridizes all 4 of its orbitals,
Okay.
and it becomes sp3.
Okay.
If we think of acetone, hydrogen places its electrons in 3 regions, a double bond, and 2 lone pairs. So 3 regions will minimize its repulsion with sp2. And then carbon monoxide,
And that would be sp2? No.
it's only got 2 regions,
Oh.
S.
One doesn't count. SP.
That's right, this is carbon's region,
Oh, okay.
sp.
Okay, okay, that makes sense. So it's just based on the regions. Okay.
That's
okay,
right.
That makes sense. Okay.
And you can count 1, 2, 3, 4, 1, 2, 3, 4.
Okay. Okay. Yes. That's all I wanted to verify.
Good,
Okay.
good work.
Awesome. Thank you.
And the same goes for carbon. You know that example we had where carbon had a positive charge, which meant there was no hydrogen and there was no lone pair. So that carbon has 1, 2, 3 regions, sp2. What geometry does it have?
Trigonal plane.
Trigonal planar. That's a flat carbon.
Okay. Perfect.
Good.
Yeah, that makes sense.
Is this online?
No, it's not. Thank you. I knew there was something I wanted to do.
Professor Flood, does that, like the size thing, what are like the limitations of that? For example, nitrogen and bromine are pretty much the same.
Yeah. But you know what? Nitrogen and bromine don't really bond to each other that often.
Okay, so it maybe has to do with carbon bonds to just.
That's the priority in our class. I did want to show you this NO bond because there are common bonding patterns. We'll see functional groups that involve NO, and I do want you to be familiar with it. I don't want you guys to think that NO is a non-polar bond. they are right next to each other after all. So I can see why you would think that. However, you don't see a lot of oxygen to halogen bonds. You don't see a lot of nitrogen to halogen bonds. So thinking about their charge distribution isn't super important. There is a common molecule, actually, that you do see a carbon to, or a nitrogen to bromine bond. It's called N-bromosuccinimide, and it's used in bromination reactions. But a lot of times we abbreviate the structure, you never even see the bond. So it's another case of, it's there, it's something you do deal with, but you don't really have to think about it. And so because of that, yeah, the charge, the size difference is also going to impact the charge distribution. I made a mistake and put this worksheet in my other class. That made it really hard to print when I was looking for it in the wrong spot.
Polarizability?
Isn't that a fun word?
It's lengthy. When I think of fun, I think of rambunctious.
That's a long word.
But it's fun.
Can you spell it?
I can spell it. Are you going to make me spell it?
Sure, I can't spell it.
RAMBUNCTIOUS.
I think I missed a C that you said. No? Rambunctious? It's a silly looking word, isn't it? It feels, I don't know that I've ever seen it written out. Something feels wrong about it.
It's the unk.
But what would you do with the N? You can't take it out. It can't be rambunctious. I think the N is a swallowed N, kind of like being, doing. You don't really say the, you don't really see the N. Rambunctious. Language is a weird thing. All right.
How was the protein powder?
I haven't had it yet. But I'm gonna, yeah, we're gonna have it tomorrow.
Well, I'm scared you're not gonna like it if you want chocolate.
Well, but it's brownie.
But no, it's not that good.
I do like brownies. Brownie batter especially. Yeah.
I think it tastes that much like brownie batter.
Well, we'll find out. I'm excited. All right. Intermolecular forces, often abbreviated as IMFs. Oops. Can you tell me why we need to clarify that this is forces between molecules as opposed to what? Yeah, like between atoms within a molecule. So we have covalent bonding, polar bonds, nonpolar bonds. We have ionic bonding, but ionic bonds are almost better thought of as intermolecular forces because they are kind of their own distinct units. They can be pulled apart pretty easily by solvents. So in intermolecular forces, and it is a bit of a misnomer because one molecule, if it's long enough, can actually wrap around and interact with itself, not by covalent bonding, but by intermolecular forces, technically within the same molecule. So it does have some contradictions. But for the most part, we think of this as two molecules coming close to each other. How do they interact? What special characteristics of those little magnets do you get? And this compounds with our idea of partial charges and polar and nonpolar bonds. So the first force is called dispersion. It's also called London dispersion. It's also called van der Waals with 2 A's. Is it with 2 A's? I don't know why my... Yeah, it is. Oof. First I messed up on the difference in electronegativity and then van der Waals. I don't necessarily like things that are named after people because it doesn't really tell you what's happening. So dispersion works a little bit better at explaining why the force exists. At any given time in a molecule, let's say this molecule, its electron cloud, which I'll show as kind of this 3-dimensional shape, its electron cloud may not be uniformly distributed. At any given time, those electrons may just happen to largely show up on the right-hand side of this structure, leaving less electron density on the left-hand side. This is not bond polarity, but now molecular polarity, how electrons are distributed in the molecule at large. So even a molecule with no polar bonds can experience this molecular dipole. But it's instantaneous. It happens for a second, less than a second, and then it's gone. And then it shows up somewhere else. So this is a very weak force experienced by everything. And it increases with increasing surface area. I'm abbreviating surface area there as SA. The larger the structure, the more surface area. You can really think of van der Waals forces as friction. If we can say that this little case I've got is made out of the same material as the bottom of this. I don't think it really is. This has got foam on it. But let's just say that it is. If they're made out of the same material, then they have the same interaction with the table. But it's not going to take a lot of energy for me to push along this small case. It doesn't have a lot of surface area interacting. It doesn't have a lot of that friction. But this larger material, it takes more force for me to push. It has more friction because it has more surface area. In the case of these molecules, that friction is magnetic attraction between partial charges. One molecule has this instantaneous dipole that points one way. One molecule has an instantaneous dipole that points the opposite way. And now they have an attraction. And so to move past each other, they have to overcome that attraction. They have to, like magnets, have enough energy to break past each other. And because this is instantaneous, because it only exists for a moment before it changes, that's not hard to overcome. It doesn't take a lot to get past. So I want you to look at this first two structures on your sheet. And I want you to decide which of those molecules do you think experiences more van der Waals forces in a pure sample, and which experiences less van der Waals forces in a pure sample. Does this have a stronger intermolecular force with itself, or does this? What do you think? If this molecule were in a sample surrounded by other versions of itself, and this were in a sample surrounded by other versions of itself. Which one has stronger interactions within itself? The one on the left. It's larger. It has more carbons. Those carbons are actually spread out more. So it has increased surface area, larger chance for these dipole moments to appear, more opportunities for those magnetic attractions. Okay. In general chemistry, you might have learned that everything has these van der Waals forces, but things that are nonpolar only live here. For the most part, things that are nonpolar are going to be mostly hydrocarbon chains, no heteroatoms. So those heteroatoms that start to create permanent dipoles, which leads us to the second intermolecular force, dipole-dipole forces. This requires at least one polar bond in the molecule plus a molecular dipole. These two compounds, CH3Cl and CCl4, they both have at least one polar bond. The CCl bond is polar. But the molecule on the left is a polar molecule because that one CCl bond is asymmetric in the rest of the molecule, and it pulls electrons towards itself away from all the hydrogens. The molecule on the right is a nonpolar molecule because all four of those chlorines symmetrically pull electrons away from the carbon. So the molecule at large has no dipole. A nonpolar compound can't experience dipole-dipole forces. No dipole-dipole attractions, only van der Waals. Right? It can feel easy to say that increasing polar bonds should increase dipole-dipole forces. Largely, that's not true. The way that polar bonds are distributed in a molecule makes a big impact on its molecular polarity. We're just not going to get into it very much. You're going to see a lot of compounds that have polar bonds. And in general, those are going to be polar molecules. So you should feel comfortable identifying polar bonds and then identifying that it will experience dipole-dipole forces. So let's look at this second set of compounds. What forces are each compound capable of experiencing in a pure sample? And what forces do those two samples have in common? Who can name the forces listed in this compound? It's very easy. Jordan. Van der Waals. That's it. Experience nothing but dispersion. And what about in this compound? Van der Waals, always. Does this experience dipole-dipole forces? Yes, because it has that one polar bond between C and O. So when molecules of this compound come close to each other, they align with each other so that their partial positives and their partial negatives line up. Partial negative to partial positive to partial negative. So here's the question. What intermolecular forces do two pure samples of these compounds have in common? Just van der Waals. They both experience van der Waals. That's it. And if you mixed these two compounds with each other, they would only experience van der Waals between each other as well. Our next strongest force is hydrogen bonding. A bad name, because it is not a bond. It is an intermolecular force. This has two requirements. It requires a lone pair on fluorine, oxygen, or nitrogen, and a hydrogen on fluorine, oxygen, or nitrogen. Both things must be true. It's not just hydrogens that are responsible for hydrogen bonding. It's hydrogens that are bonded to fluorine, oxygen, or nitrogen. Sometimes I give this graphic that says if a hydrogen is bonded to one of these atoms, then it can interact with the lone pair on one of those atoms. And I do this to show that it doesn't need to be a specific combination of what atom's lone pair and what atom is bonded to the hydrogen. It can be any possible present combination of those things, right? Okay, the third set of compounds. Do either of them experience hydrogen bonding? In a pure sample of the compound on the left and the compound on the right, do either of them experience hydrogen bonding within themselves? Which one? On the right experiences hydrogen bonding. It meets the criteria of having OH, and we know that that O has lone pairs. So this can hydrogen bond with itself. The partial positive on the hydrogen lines up with the partial negative on an adjacent oxygen. Does that compound on the right also have dipole-dipole interactions? Yeah, in fact, hydrogen bonding is just a specific example of dipole-dipole. It's a very strong dipole-dipole. It's just dipole-dipole. But it also has CO bonds, and those CO bonds can have dipole-dipole interactions between molecules. Compound on the left, does it experience hydrogen bonding? No. Does it experience dipole-dipole? Yes. So what forces are shared between pure samples of these compounds? Always dispersion, and then dipole-dipole. All right, the last one, and this is a bit less common, is dipole ion forces. This becomes more relevant when we start doing actual chemistry, and we want our solvent molecule, like let's say water, we want it to solvate our ions. So this is an organic ion, NaOCH2CH3. And water has these partial positives on hydrogen that will interact with the anion. And oxygen holds a partial negative that will interact with the cation. So this ion to dipole attraction is helpful in getting salts to separate from each other. Ion-ion is stronger than ion dipole, but ion dipole is more plentiful. If I take a gram of this salt and I dissolve it in a liter of water, I have far more water molecules that can do lots of little ion-dipole interactions and break apart the ion-ion force. It's a cumulative effort. But this is one that we just won't show quite as often. These other first three are more common. So here's what I'd like you to spend another 5 minutes on. With this bottom row, if you haven't already, identify what intermolecular forces are present in each compound, and then tell me what IMFs are common between the two molecules. Feel free to work with each other. 5 minutes on this, and then we'll move on.
Because the oxygen is more electronegative, therefore
What are you thinking, Lean? What do you think? Identified some hydrogen bonding, yeah? How about this? Can it do any hydrogen bonding? How come? It's the right answer. So now we just have to feel confident in it. What's required for hydrogen bonding? Bonded to the H. And there is no H bonded to O, N, or F, right? Good. Does it have dipole-dipole? Any polar bonds? What are you drinking, Christine?
I have banana, this like protein strawberry drink,
Mm.
and then I put a persimmon in there. Have you ever had
Yes, yes, just recently for the first time. Looks like a little orange tomato.
Yeah.
I liked it more than I thought I would. Yeah, yeah.
And then chia seeds.
Nice. Chia seeds, I've heard, or I watched a guy that does mukbang videos, like just overeating videos. And his mom sent him chia seeds, and he just like chugged a glass of them, wrecked his stomach. And so he did it again because he thought maybe he did it wrong, wrecked his stomach. And then he said, oh, they're supposed to soak in hot water for an hour at least.
Yeah, I just do mine overnight.
Mm.
And with some milk or something.
Sure. Kind of want to try it.
Yeah, you should. They've got to like, I don't know, add texture to things.
Yeah, totally. Sometimes that texture throws me off. Boba? I can't do the boba texture, no. All right, let's wrap up this section. Do you guys agree that dispersion forces are present in all of the molecules? Great. I am going to abbreviate it as VDW for van der Waals, but if you want to abbreviate it as something for dispersion, go for it. So it doesn't really help except establish a baseline, and anything that doesn't experience more than van der Waals, that will be the only thing common in that sample. Okay, my first molecule, does it experience dipole-dipole forces in a pure sample? Yeah, the CO double bond is polar, so that polar to polar bond gives us, I'm going to abbreviate this as dip-dip. Does it experience hydrogen bonding within itself? No. There's no hydrogen bonded to an oxygen, nitrogen, or fluorine, despite there being a lone pair on the oxygens. So within itself, no hydrogen bonding. All right, the molecule on the right, dipole-dipole? Yeah, for two good reasons, CO double bond and CO single bond. What about hydrogen bonding with itself? Yeah, that OH can hydrogen bond with a lot of different lone pairs. Sorry, I'm going to call this H bond. It can, the OH can hydrogen bond with a lone pair on another OH oxygen or the lone pair on a CO double bond oxygen. So there's a lot of opportunities for hydrogen bonding. So comparing two pure samples, what is the strongest intermolecular force that they have in common? Dipole-dipole. A pure sample of the compound on the left has dipole-dipole, and a pure sample of the compound on the right has dipole-dipole. Another way of approaching this question is to say, if these two molecules were mixed together, what is the strongest intermolecular force that they would experience between themselves? What do you say? What's the strongest intermolecular force that these two molecules coming together could experience? Dipole-dipole? Not necessarily. Because the compound on the right can be a hydrogen donor for a hydrogen bond, and the compound on the left can be a hydrogen bond acceptor. It still has lone pairs that it can accept electrons, a hydrogen bond through. So the strongest force that they hold with each other is H bonding. They can hydrogen bond with each other, but the compound on the left can't hydrogen bond in a pure sample. Not because there are no hydrogens, but because there are no hydrogens bonded, oh, it's gone, to fluorine, oxygen, or nitrogen. Do you guys see the difference between those two questions? Analyze a pure sample and analyze the two together. Because I often ask this question on unit tests and exams, and the easiest confusion is misunderstanding pure samples from mixing them together. So I just want you guys to understand the difference. All right, compound on the left, dipole-dipole? Sorry, yes. Hydrogen bonding in a pure sample? No. How about on the right, dipole-dipole? Yes. Hydrogen bonding? Yes. So the strongest they have in common? Dipole-dipole. The strongest they have when mixed? Hydrogen bonding. Can someone explain why these two are able to hydrogen bond when mixed together? The lone pair on the oxygens. Not a hydrogen bond donor by any means, but certainly a hydrogen bond acceptor. All right, on the left, van der Waals, dipole-dipole. CN is polar, so the CN bonds then create dipoles. Hydrogen bonding? Yes. That NH is able to hydrogen bond, and the lone pair on N is able to hydrogen bond. On the right, dipole-dipole. CO bonds are polar. Hydrogen bonding? Yes. So the strongest they have in common, hydrogen bonding. The strongest they experience with each other, boy, it'd be surprising if it wasn't hydrogen bonding, right? Okay, any questions on this?
Can you give us an example of something where they can't hydrogen bond together? Or is it
Yeah, actually these. If we mixed these two compounds together, the ones on the top there, top right, the strongest force they have in common is dipole-dipole, and the strongest force they can feel with each other is dipole-dipole. Chlorine, not fluorine, chlorine cannot donate its lone pair in a hydrogen bond. So that compound on the left is incapable of hydrogen bonding, so the strongest interaction it will have on the right is a dipole-dipole force.
So only fluorine, nitrogen, and oxygen are the ones that can donate the lone pair in that bond?
That's right.
Okay.
Only fluorine, oxygen, and nitrogen donate a lone pair for a hydrogen bond. It's not a bond for that attraction. And the hydrogen on the other end has to be bonded to a fluorine, an oxygen, or a nitrogen. So this can hydrogen bond, this cannot. So in a mixture of the two, their strongest force between each other is dipole-dipole. All right, let's move on. Resonance. Do you know what this is on the right, on the left? What? Orbitals. Molecular orbitals. It's back to MO theory. All right. We're going to talk about resonance. Can anyone give me a definition of resonance? This is a tough one to define. Layla?
It's like when the pi bonds and the lone pairs move, but the other
Good. Pi bonds and lone pairs move, and often that results in charges moving. But sigma bonds do not break. Sigma bonds are not formed. They don't break at all.
like rearranged in a different order.
Good. Rearrangements, specifically of our pi electrons. So there are two words that I like to use to describe this. Movement / delocalization of pi electrons. And again, that can be lone pairs or pi bonds. Why do I say movement / delocalization? Aren't things that aren't localized moving between those two localities? No, they don't have to. They don't have to move between. They can be in two places. That's the beauty of electrons. So movement is better described by valence bond theory. Delocalization is better defined by molecular orbital theory, which means movement is what our bond line structures will show us. Bond line structures will make it look like electrons are moving for these rearrangements. But MO theory will say that it's delocalization. It's neither one nor the other. So I want to take you back one step, and I want to remind you of how we formed a pi molecular orbital. We took a p from one atom and a p from another atom, and we joined them constructively and destructively, and we got a pi bonding orbital where they were in phase, and a pi anti-bonding orbital where they were out of phase. In theory, you can show resonance with just that. You could say, what if the electrons were not between the two atoms? What if they went to one or the other of the two atoms? But that's not a super common resonance distribution. So what happens more often is that we take this form and we combine it now with a new p orbital. So we have pi, pi star, and p. And we will join these constructively, destructively, and a little bit in the middle, which is going to result in 3 new orbitals. So we won't call these pi and pi star anymore. We'll call them pi 1, pi 2, and pi 3. From lowest energy, the orbitals will all be in phase with each other, shaded with shaded, unshaded with unshaded. So at the lowest energy, we get a new molecular orbital that is essentially just the overlap of 3 pi orbitals. If you want, you can erase this central part, which makes it look like just one big blob. But you can see on the sheet, I've given it to you as just 3 orbitals side by side by side. At the top, my highest energy orbital, all of my individual orbitals will be out of phase with each other. So I'll have p out of phase with p, out of phase with p. And these changes in phase, as always, are what we call nodes. I've gone from 0 nodes in my lowest energy to 2 nodes in my highest energy. So what you can see is that energy increases with nodes. The more nodes that are present, the higher the energy of the system. So what is my middle going to look like? Well, it still needs to span these 3 atoms. Remember, this is a molecule. Originally, we said, look at this molecule where there are 2 atoms. Now we're saying, look at this molecule where there are 3. As a molecule, the nodes will be localized over atoms 1 and 3. Oh, and I made a mistake on your sheet. Yeah, that is a mistake. Do you see how in that middle node, in that middle orbital, they're both shaded up? They should be shaded, one shaded up and one shaded down. They should be out of phase with each other. I've drawn them as in phase. Make sure you do that when you get home, first thing. Change that orbital. Okay, you guys got that? Got to keep you on your toes. What's in the middle between those 2 orbitals? If they're changing phase, it's a node. 0, 1, 2 nodes. With each increase in energy, we add a node to the system, but the node in this middle orbital falls directly over an atom. Okay, here's the interpretation. Electrons that occupy this system are not localized to any of those 3 atoms. Electrons that occupy pi 1 are found at all 3 atoms in this 3-series system. Electrons that occupy pi 2 are found at the first and the third atom, and they're never found at the central atom. If you're okay, if you're comfortable with the idea of a p orbital, where an electron is able to go from the top node to the bottom without passing through the center, because that's a node, a region where the electron is not found, then you should be comfortable saying that an electron can be found on atom 1 or atom 3, but not on atom 2. It's just passing through a node where the electron is not found. And if you think back to that idea of what waves are, increases and decreases in net zero, it's just net zero here. It's just a bit of a longer wave with this neutral spot in the middle. That's the electron. Okay, so there's some really beautiful things that come out of this, but this idea of delocalization is the important thing. It's not on atom 1, it's not on atom 2, but the electrons in this orbital are delocalized between atoms 1 and 2. If these electrons are responsible for a negative charge, that negative charge is not on a specific atom. It's delocalized between two atoms, experiencing more like a half negative charge. Valence bond theory and our structural interpretations of molecules are going to make it look like these will move between each other. But truly, molecular orbital theory says that movement is a misunderstanding of what the electrons are doing. It allows us to show when the electrons are in both places, but it doesn't allow us to show it at once. All right, here's an example. A 3-atom system. 2 of the atoms have a pi bond. 1 of the atoms has a positive charge. There is no reason that it needs to be arranged like this. So we represent a resonance arrow. That's not 2 arrows going in different directions. That's a double-headed arrow. And we show another version of this molecule where the pi electrons have been rearranged, like Perla said. Nothing happens to the sigma bonds, like Layla said. But my pi electrons are now in a different spot, and my positive charge is in a different spot. The charge seems to have moved from one atom to the next, but it's actually just delocalized. So we show a resonance hybrid. A 3-atom system, that's a pretty ugly positive charge. A 3-atom system with this positive charge and a double bond across all 3 atoms. This is also a little bit misleading. It better represents the fact that the central atom has a double bond with both exterior atoms because it shows this circle showing a double bond across all 3, like this orbital says. But it also says there's a positive charge. Where is that positive charge? This might make you think the positive charge can be on the central atom. MO theory says it can't. So this helps justify MO theory, but it still doesn't do a great job. Let's look at another case. Instead of giving a positive charge there, let's have a lone pair and a negative charge. We see a similar setup. The lone pair moves between atoms 1 and 3, as does the negative charge. The pi bond moves, but truly neither of these represent the structure. Instead, it's more approximately equal to this double bond across all 3 atoms with a negative charge held. And this doesn't do it justice either, because this might lead you to think the central atom can hold the electrons, but truly they're just delocalized across 1 and 3. These are what we call resonance forms, the individual Lewis structures, and then a resonance hybrid, the combination of those resonance forms. Not all resonance forms are equal to each other. So we have rules for ranking and understanding the stability and the contribution of resonance forms. Three rules. Rule number 1, minimize charge. Have the least amount of charge possible in your structure. I've given you 2 molecules at the top here. where I want you to show resonance forms and predict which one minimizes charge. First, we'll take this CO double bond. Oxygen owns the electrons of the pi bond. So if the pi electrons are going to move, they're going to move how oxygen decides. Oxygen is more electronegative. So oxygen wants the electrons. So the other resonance form possible here is when the pi bond moves towards the oxygen and away from the carbon. Which resonance form is more stable? Which is a major contributor to the molecule? The form on the left, because it has minimum charges. So we say this is a major contributor and this is a minor contributor. It helps us understand things like the partial charge between carbon and oxygen. But when you think of how the molecule behaves, it behaves with minimum charges. Okay, the second structure that I gave you, this is what we call a bicyclic molecule. It has 2 rings in it. And there is a resonance form, I'm going to have to draw this kind of strange, where nitrogen at the top is able to donate electrons to the pi bond down below. Nitrogen at the top takes its lone pair, it shares it to create a double bond with carbon, and the double bond of carbon breaks to the other nitrogen. Well, now I have charges. The top nitrogen has shared electrons to create 4 bonds, positive charge. The bottom nitrogen has now accepted electrons and only has 2 bonds, negative charge. So which of these is a more major contributor? Which of these is more stable? Top one, with no charges. That's our major contributor. By the way, if you're a little bit confused about drawing it, look down below. I've given that to you again, and I'm going to help you guys practice with how to use arrows to describe how these bonds are changing. So if you need to copy that one down, it's down here. All right, rule number 2. Any questions before I just jump along? Rule number 2, maximize octets. Oh my God. Well, why didn't anybody say the time was gone? You know what almost always happens with maximizing octets? It's carbon's fault. Carbon has a positive charge and it doesn't have octets. So another way of saying this, maximize octets, typically means make 4 bonds to carbon. I want to give you guys some examples for that. But the third rule, and I'll give this to you before you go so that you can practice on some of this and get a head start on section 2 homework. These are priority based. So first you minimize charge, then you maximize octets, then you have appropriate charge placement. What does that mean? Well, it means if you have a negative charge, it should be placed on the more electronegative atom. More electronegative takes the negative charge. If you have a positive charge, it should go on the least electronegative atom, not including carbon, because when carbon takes on a positive, it doesn't have its octets. So you want to make sure that while you have maximum octets, you also place your charge appropriately. And we've got some examples down here to go through that highlight each of those rules. We'll pick up with this tomorrow. No, Wednesday. And I'm going to show you guys how to use arrow pushing to get through it. And then we have a conversation about acids and bases. I'm going to be bringing in another short worksheet on Wednesday to wrap up our acids and bases. Okay. I guess you can go. Thank you for your time. I'll see you guys Wednesday.